Hi, my name is Brian Caffo, and this is the lecture on p-values in the Statistical Inference Coursera class as part of our data science specialization. This class is co-taught with my co-instructors Jeff Leek and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. P-values are the most common measure of statistical significance. Basically, every statistical software that performs a hypothesis test outputs a p-value for you. And because they're so popular, and because often they get misinterpreted, they're quite controversial among statisticians. And so what I give here are some comments both in favor of and some papers and commentaries against p-values. In this class, we're not going to focus too much on these controversies, but instead are just going to focus on how do you generate a p-value and how do you correctly interpret it. The basic idea of a p-value is to start under the null hypothesis, assume that nothing is going on, and then calculate the probability of obtaining evidence as or more extreme than we actually obtained under this null hypothesis. Basically, how unusual is the result we got if the null hypothesis is true. So let's go through the approach through maybe 3 simple steps, and then we'll go through basic calculations in the next set of slides. So first of all, you get the hypothetical distribution of a data summary, which we'll just call a statistic, like our test statistic from the T lecture, and figure out its distribution when nothing is going on, the so-called null distribution of the statistic. Then we calculate the statistic with the data that we actually have. So for example, we calculate our T statistic. We actually plug in the empirical mean, subtract off the hypothesized mean, and divide by the standard error. Then we calculate the probability of obtaining a statistic as or more extreme. In other words, we compare what we calculated to our hypothetical distribution and we see how extreme it is toward the alternative. So if the p-value is small, what you're saying is the probability of observing a test statistic as extreme as we saw is low if the null hypothesis were true. Okay, let's go over p-values with a little bit more formality. So the p-value is the probability under the null hypothesis of obtaining evidence as or more extreme than was actually obtained. So, and usually we're talking about evidence here in terms of the test statistic. So it's the probability of obtaining a test statistic as or more extreme in favor of the alternative than was actually obtained. So if your p-value is small, then either the null hypothesis is true and you've observed something that is highly supportive of the alternative that was quite unlikely, or the null hypothesis is false. So let's go through a quick, just numerical example. So we've covered the T statistic and simple t-tests. So imagine if you wanted to test mu equal to mu naught versus mu greater than mu naught, and our T statistic worked out to be 2.5 on 15 degrees of freedom. What is the probability of getting a T statistic as large as 2.5 in this scenario? Well, here we can calculate it. It's just PT, 2.5, and 15 for the degrees of freedom. We want lower dot tail equals false because we want the probability of being larger than 2.5, right? As or more extreme in the direction of the alternative. And that works out to be about 1%. So therefore, the probability of seeing evidence as or more extreme than actually obtained under the null hypothesis is 1%. So either the null hypothesis is true and we've seen an exceptionally large T statistic, or the null hypothesis is false. So there's another way to think about the p-value as the so-called attained significance level. And let's go through that really quickly. So recall we went through an example where our test statistic was 2 for h naught mu equal to 30 versus mu greater than 30. So test statistics larger than 2, or I'm sorry, test statistics that are larger are going to be more supportive of the alternative. Where 2 here is that our test statistic was 2 standard errors above the hypothesized mean of 30. Let's assume that our test statistic is standard normal distributed rather than t-distributed, just to make our discussion a little bit easier. Now, if we were to set alpha equal to 0.05, we know that we would reject because we know the rejection region and the quantile that we would reject for at 0.05, so that area was 0.05, would be, the quantile would be 1.645. Since we know 2 lies above 1.645, we would reject. Now imagine if instead of 0.05, imagine if we did 0.04. Then we would have another line that was a little bit closer than 1.645. So what if we were to find the exact error rate where the line fell exactly on 2? Well, that would simply be calculating this probability right here of 2 or larger. And that's nothing other than the p-value. We just did that calculation. That's the probability of getting a test statistic as large or larger than 2 under the null hypothesis. So at any rate, another way to think about the p-value is it's the smallest value for alpha for which you would still reject the null hypothesis. And so because of that, they call it the attained significance level. And what this means is that the p-value is an extremely convenient test statistic to communicate to people, because when you give it to them, they can test it versus whatever alpha level they would like. Let's reiterate some of the points we made on the previous slide. So by reporting a p-value, your reader, or whoever you're giving the p-value to interpret it, can perform the hypothesis test at whatever alpha level he or she chooses to. The simple rule is, if the p-value is less than the alpha level, then you reject the null hypothesis. If the p-value is greater than it, then you fail to reject. Now we calculated our p-values for one-sided hypothesis test, T and Z test. In order to get the two-sided hypothesis test, you have to account for the evidence as or more extreme too large, or as or more extreme too small negative. So because the equal probability in either tail, you wind up doubling the p-value. I would give a cautionary note that the software automatically interprets, for most tests, automatically interprets the test as a two-sided test. Most of the time they'll denote this as p-value for a two-sided test, but if they don't, they're always calculating the p-value for a two-sided test. The other thing I would note is that if you happen to take some more advanced classes in statistics that cover things like chi-squared test, those p-values are automatically, in a sense, two-sided. You would not have to double them. Okay. Let's go through some more examples of p-values from some different circumstances other than T or Z test. So we actually covered an instance of a p-value previously in the class, and I wanted to go through it again now that we know what p-values are. So suppose we're going to think of gender assignment for kids, that we're going to think of this for a specific couple as if it's a coin flip. Now there's a lot of complexity to this problem and we're going to reduce it, but let's just assume that it's a coin flip. And what we're wondering, because you have a friend that has, out of 8 kids, had 7 girls, whether or not the probability that that coin lands on girl, right, let's say P is the probability of having a girl, is equal to 0.5 versus greater than 0.5. So the null hypothesis is H naught P equal to 0.5, and the alternative is HA P greater than 0.5. Well, under the null hypothesis, we want to calculate the probability of getting evidence as or more extreme. Now we don't know what the test statistic is in this case, but the most logical one is just the count, the number of girls out of the 8. So 7 or 8 would be as or more extreme than was actually observed. So the p-value calculation is the binomial calculation for 7 plus the binomial calculation for 8 under the null hypothesis where p is 0.5. That works out to be about 3.5%. I also go through the calculation here where I do p binom instead of directly plugging into the binomial formula, and of course you get the same number. If we were testing that hypothesis, we would reject at a 5% level. We would reject at a 4% level, but we would not reject at a type 1 error rate of 3%. Now I would mention on this specific problem, it's not obvious what the two-sided p-value is, though I'll give you a simple trick. And the simple trick in this case is to simply if you wanted to test whether p is 0.5 versus p different from 0.5, then you just calculate the two one-sided p-values. In this case, the probability of being 7 or larger would be one-sided p-value, and the probability of being 7 or smaller would be the other one-sided p-value. You take those two one-sided p-values, you take the smaller one, and you double it. And that's the procedure for getting a two-sided p-value in these exact binomial calculations. Let's go through a Poisson example. So suppose a hospital has an infection rate of 10 infections per 100 person days at risk for a rate of 0.1 infections per person day at risk during their last monitoring period. And we want to assume that a rate of 0.05 infections per person day at risk is an important benchmark. If the rate goes above that, they would implement some quality control procedures, let's say. But you don't want to just have these expensive quality control procedures go into place just because of random fluctuations. So you'd like to formally test this hypothesis, accounting for the uncertainty in the data. And here we're going to assume that the number of infections, is Poisson. Well, the null hypothesis then is that lambda is 0.05 versus the alternative that lambda is greater than 0.05. Or, given that we're specifically talking about 100 person days at risk for this particular monitoring period, we could think of this as the null hypothesis is that the rate times 100 is 5 versus the rate times 100 is greater than 5. So what we want to know is if in fact the rate is 0.05, having been monitored for 100 person days at risk, what's the probability of obtaining 10 or more infections? Okay, so this is a Poisson probability. We want the upper tail, so remember this little quirk of R, if you want the upper tail and you're doing a discrete distribution, you actually have to drop the number down by 1. So we want PPOIS, so P-Pois for the Poisson probability. We want to put in 9 because we want the upper tail and because of this issue that it does strictly greater than for the upper direction. Then the Poisson rate is 0.05 times the 100 person days at risk, so 5. And then we want to specify lower.tail equals false to make sure that we don't get 9 and fewer, but we want strictly greater than 9, which is 10 or more. And that will give us our relevant p-value. So what is this probability? This is the probability of obtaining 10 or more infections if in fact the true rate of infections we should have seen on 100 person days at risk is 5. Okay? And it turns out that that's a relatively low probability. It's unlikely for us to have seen as many as 10 infections for 100 person days at risk, only 3% chance of that occurring if in fact the real infection rate was 5 for 100 person days at risk. So this hospital perhaps should execute those quality control procedures. So hopefully what you've gotten out of this lecture is that the way that you calculate a p-value is you calculate the probability of obtaining data as or more extreme than you actually obtained in favor of the alternative where the probability calculation is done under the null. And all the p-values are done this way, and I think what we saw was the kind of formal rules that you could execute in the z and the t-test, which are kind of easy, but then we logicked our way through some of these other examples, like the binomial example and the Poisson example.